Morning, Mr. Robinson.
Good morning. How's it going?
Good, good.
Hey, Mr. Robinson.
Hey, good morning. How's it going, Edgar?
Good. Good.
Morning.
Good morning. Oh, wow. Yeah, y'all must be bored. Everybody logs on pretty quick. Okay. So today, like I said, we're going to try and keep stuff going pretty regular. I got two parts to today's warm-up for you. Item number one, 2 people are 2 meters from you, right? Since that's the CDC recommended inner distance between human beings as we go out in public in these times. And one is at 12 o'clock and one is at 7 o'clock. So just so you know, I mean like tactical directions, the way that pilots use when they're referring to the positions of other airplanes. Talking about clock position is nice just because it gives you a really quick reference for angles. That is to say, one is directly in front of you, which is 12 o'clock, and then one person being at 7 o'clock means that they are behind you and this way. So that is to say, you have one person that's 2 meters this way, one person that's 2 meters this way. My question for y'all to calculate real quick is use the law of cosines to figure out how far apart they are from each other. You'll have to, of course, take the relative clock angles, right, 12 and 7, and use those two in order to figure out what that is in terms of a physical angle. But just think of it this way, right? How many degrees are in a full circle?
360.
360.
And there's 12 hours, right? So if you take 360 and divide it by 12, it'll tell you how many degrees there are between each hour. Do that first. And then item number 2, podcasts, since we're all, stuck at home doing either school or other stuff, right? I have some podcasts that I'd like to recommend, some stuff that's good, not political stuff, of course, but just regular old podcasts to get you through these times. Anyway, do this first law of cosines question, and then that'll actually be the last trig anything that we're going to be doing for a long time, because today we're switching gears into chapter 9, which is nothing to do at all with trigonometry. And in fact, we won't see trigonometry again until we get to the end of the school year and we start doing our final review. Any questions out there?
Mr. Robinson, from 12 o'clock to 7 o'clock, isn't that more than 180 degrees?
It's actually, it's just less than 180. I mean, it depends on which way you count. If you start at the top, and actually, I don't know if
Yeah, because maybe it should be like 12 to 5. Like, Because if you're saying 12 to 7, it's going like 180. It's like 12 to 6.
The physical angle between 12 o'clock and 7 o'clock is the same as the physical angle between 12 o'clock and 5 o'clock. They're just in different directions. So if you do the trig, they should come out exactly the same.
Okay, cool. Thank you.
Yeah, that's a good question. Good question.
Mr. Robinson?
Yep.
Is it an isosceles triangle?
It is, yeah, because this is like one of our common examples that we've dealt with where if you're talking about a triangle formed by the radii of a circle, since those two sides have to be the same, then yeah, it is an isosceles triangle. Both of the lengths will be 2 meters.
Okay, thank you.
Mm-hmm. And then let me go ahead and take attendance real quick. Tight. Perfect attendance. I guess that's really easy to do when we all get to like stay home, you know? In fact, I've been pretty excited that I can like, normally when we're at school, right, I have to, I don't know, get ready at like 7:15 and be out the door by 7:30. I've been getting ready at 7:50 and I've still been on time for first period. Small victories. Okay. Y'all ready to begin? It is on the correct capture, right? Yeah, y'all can see. Okay, cool. Yeah, thanks for the thumbs up, y'all in the chat. Okay, so let's just go ahead and start off first with podcasts. Could y'all give me a thumbs up if you listen to any podcasts? Are y'all into that yet? Yeah, some of you. Let me grab my phone. It's like charging behind me because my battle station has so much stuff plugged in there. Just in case y'all want some stuff to help get you through these times, here are my like appropriate for school non-political podcasts that you might get something out of. The first one that I'm going to recommend is called 99% Invisible. I think I've recommended this one to y'all before. It's a podcast about design is the official reason for the podcast. Like that's their official description of what it is the podcast is about. But under that, guys, it's actually about anything that the host thinks is interesting. So recently they did an episode on like the global infrastructure that makes predicting the weather possible. That was a really good episode. They also did a really good episode about the font Fraktur, F-R-A-K-T-U-R, which is like the classical looking German font, and about how it's weird that that is associated with Nazi stuff in contemporary culture, considering Hitler personally hated that font. Just a bunch of random stuff like that of like, hey, how do these design choices affect the world? It's really good, and I would recommend if you're going to listen to it that you go back to their episodes from November. They did a mini series within the podcast called Articles of Interest, where they talk about the development of clothing and clothing styles in the modern era. It's really, really good stuff. The other two that I want to recommend for y'all today is stuff you missed in history class. It's a really good podcast, and it's so long that they actually had to change hosts at one point as the podcast went from control by one company to another. And so because it has such a deep back catalog, I guarantee if there's any thing in history that you want to learn about, they probably have an episode about it. It's really good. It's really well produced. And then the last one that I'm going to recommend for y'all is called Science Versus. It's a science podcast hosted by this Australian lady with a master's degree in, I forget which type of engineering, but she has a classical science training. And the reason why I recommend it is not only because it's very good and they have a lot of diverse episodes about various science topics, but of course, like all other science podcasts, they've switched over to all coronavirus coverage all the time, which is what their most recent episode is about, in case you want a more sober look at the outbreak than probably what you'll see on cable news. And they had a really uncanny thing where a few months ago, like last summer, they did a fictional what if episode about what would happen during a pandemic. I would check that out in case you want a scientist's take on what's going on. It's a really good collection of thoughts. Anyway, let's go ahead and get started with our math warm-up today. And so just to draw this really nicely for y'all, let's go ahead and say that we have a person here. This is going to be the center of our question. And the person at 12 o'clock is 2 meters ahead of us, which I'll draw out here. So that person is right there. And because this is taking place along a circle, right? Because these two people should be equidistant from us. And this is a trick y'all should get used to for the SAT. Simply because they think it's very clever to ask questions involving triangles on circles. The trick is that they can give you less information than normal, just because we know that all of the lengths of all radii must be equal to themselves. So instead of giving y'all 2 lengths, they give you 1, and they just implicitly expect you to know that both of them are equal. So this length here is 2 meters. So that's 12 o'clock, 6 o'clock. So 7 o'clock would be a little bit back this way. And so this person is also 2 meters away. And if we remember our old school geometry marks, you got that mid-segment mark, shows that they're congruent. And so my question is how far apart are they? What is this length from here to here? How far are they standing from each other? So could I get a volunteer real quick, right? What do we expect our answer to be, and what ballpark should it be?
Some big number, I'm guessing. Should be
Well, it should be larger than 2.
It definitely should be larger than 2, but we can also set a lower limit on it. I'm sorry. Yeah. It should be larger than 2, which would be a lower limit. We can also set an upper limit on it. We can definitely say that our answer must be smaller than some specific value. Look at the circle. Think about it.
Diameter.
Yeah, it has to be just smaller than the diameter. And this is also a true feature of all these weird circle type questions. So if they were both pointed in the same direction, that distance would be 0 between those 2 people, which would be against CDC guidelines. And at maximum, they would be at 4 meters apart from each other. So our answer has to be somewhere between those 2 potential values, where if they're pointed in the same direction, the distance between it is 0. And then as we rotate out, the distance increases to a maximum possible value of 4. So we'll know that we did something right here, so long as our answer is slightly less than 4. Did anybody figure out the angle? So first off, how many degrees are between each hour?
30.
Yeah, it's going to be 30, just because it's going to be 360. Hey, tell me, y'all watching at home, are those green pixels?
Yeah.
Do y'all see some dead
yeah.
pixels in my webcam?
Oh, yeah.
Okay, so that's on the screen. That's not my actual laptop screen. Oh, wait.
It's like right in the middle, kind of.
Yeah.
Wait, you see those? You see like a couple random dead green pixels?
Yeah.
Mhm.
Oh no, I hope my webcam's not dying because it's really hard to order a new one of those right now.
Uh-oh.
It's not that noticeable though.
Yeah, no,
I-
it's fine.
Yeah, I shouldn't have pointed it out. Now I won't be able to unsee it. But hey, anyway, 360 divided by 12 means that, yeah, there's 30 degrees of separation between each one of those angles, which is why it's like a nice, convenient way to talk about directions when you're out in the world. And between 12 and 7, there's 5 hours. That is to say that there's 150 degrees of separation between those two. Is that okay?
Right.
Okay. So this angle here, that's 150 degrees. And so we hit this with the law of cosines because this is an SAS orientation of information. This is to say, if we want to know what direction, how much distance is between these two people in terms of meters, c squared is going to be equal to a squared plus b squared minus 2ab cosine of c. And when we're solving for that opposite side length, instead of going through a bunch of fancy manipulations, all we have to do to isolate c is a single step of algebra. What is that step?
Square root.
You can take the square root of both sides. This is to say c is equal to the square root of a squared plus b squared minus 2ab cosine of angle c. And please keep in mind that there is no simplification that can occur here, even though these are squared and they are on the inside of a square root, because these are being added first. There is no arithmetic substitution. I'm sorry, there is no algebraic simplification that can occur. And so the rest is plugging and chugging. So c is going to be equal to the square root of 2 squared plus 2 squared minus 2 times 2 times 2, which is 8, cosine of 150 degrees. And so if we take this and we turn the crank on it, this will give us our answer. So it's going to be equal to the square root of 4 plus 4 minus 8 cosine 150. Close the parentheses on the square root. And the distance between these two is 3.86. And how do we know that this is a pretty good answer?
It's less than 4.
It's in between 2 and 4, but it's bigger than 2.
Yup, it is just a little bit less than 4, considering it's a little bit less than the diameter. So please keep in mind that when it comes to equidistant questions or triangles that would fit well inside circles, they're usually asking you to use some law of cosines information because we got SAS. By the way, just so y'all know, if you have any standardized test prep to show me, Q3's gradebook is still open in case you want to get that in before grades are taken at the end of the week. So feel free to email that to me directly. Just call it standardized test prep. And also, if you need help with standardized test prep in case you're still prepping for the SAT, the ACT, anything like that in the days to come, let me know and we could set up like a one-on-one meeting or whatever, or do a group discussion in case y'all need help with SAT math. Is that stuff okay?
Yep.
Cool.
Yep.
Okay, so let's go ahead and get to section notes for today. And boy, is this going to be a relief to y'all who might not have read ahead in the book or flipped forward to see what we're doing next. The difficulty of this class for most of y'all is about to go from like a 9 or a 9.5, whatever trig was, all the way back down to like a 3 or a 4 difficulty for a while. Today we're going to be doing a review of old skills just because they need to slot nicely into our new skills that we're going to be learning. We're going to be learning how matrices behave and how to do matrix manipulations. However, matrices themselves, oh, hey, Boogie. Hi, how's it going? Come here. No, come here. She doesn't want to come. Anyway, because those skills slot nicely into our linear equation skills. So today we're going to do a review of what it is to talk about a system of 2 variables, 2 equations, how to solve it. Most of y'all are like so good at that you could never forget it again if you tried, right? And from there, we're going to learn how to solve systems of 3 equations. We're going to learn how to solve nonlinear systems, and we're going to learn how to solve systems of inequalities. Those are going to be the 4 sections that we cover before our mid-chapter quiz. And then after the mid-chapter quiz, we will get exclusively into matrices and matrix operations up until the end of the chapter. Did y'all do matrices before in Algebra 2? Did y'all touch on that?
Yeah.
Mm-hmm.
Yeah. Y'all probably took matrices and used them to solve. You also probably added, subtracted, multiplied them. Yeah?
Yeah.
Mm-hmm.
Did you happen to deal with determinants?
Yep.
Oh, okay, cool. Then
Also,
okay, sweet. Then I guess for some of y'all, the chapter in total might be review from end to end, but you know, that's for a reason. Math classes are usually a little bit redundant in the important stuff they want you to cover, just because the way in which we're going to talk about the skills is going to be different than the way that y'all talked about them in Algebra 2. Anyway, today we're going to talk about section, I got to restart the webcam, that's going to bug me. I'll restart it before next period. Today we're going to be talking about 9.1. Hey, Boogie, get out from there. Nope, get away from the power cords. Hey, go, nope. Sorry, 1 second. Cat emergency. Look, don't touch the power button. Hey, get away from the power strip. Come here. Hey, you. Oh, look, it's a cat. Okay, now go away. Hey, anyway, today we're going to be talking about 9.1, systems of linear equations and two variables. Which I'm just going to call 2D for right now informally, because whenever you have variables in some kind of system, those themselves are referring to various sets of dimensionalities. And I guess that's like kind of a physics-y take on it. That is to say, when we're talking about graphs in the X and Y in a flat space, right, you can only move in this plane defined by the pen. However, there is no way in or out. There is no third dimension. You and I live in a 3D space where we have access to move in the X direction, the Y direction, and the Z direction, and all three of these are independent of each other. However, mathematically, you could lose your mind and you could create some sort of math setup that has 4 variables instead of having just X, Y, and Z. You could have W, X, Y, and Z. And even though you can't really draw or try to imagine what that 4th dimension is, the math works out exactly the same. And when we find ourselves doing physics, there are cases where we work in higher dimensionalities, and those answers that we get back from that math, they have real testable predictions in the real world. And I mean, this might mess you up. We even have math that describes how to deal with infinite dimensional sets, places where you could have an uncountable number of independent ways to move with respect to each other. Nonetheless, we're going to start it off not infinite dimensional, not even 10-dimensional, just 2-dimensional. So when it comes to systems of linear equations in 2D, this is to say that I have 2 linear equations. And just because we're so used to slope-intercept form, we'll keep it in that form. So that is to say that I have some pair of equations, y is equal to ax plus b, and y is equal to cx plus d. And when it comes to this pair of linear equations, there are 3 different ways that this scenario can play out. And so to talk about it in a perfectly straightforward way, give me 1 second here. Okay, so can you all see the Desmos screen that I just switched over to? Can you all see that?
That's
okay.
Crazy.
Okay, here I have in Desmos the 2 equations that I just wrote down, y is equal to ax plus b, and y is equal to cx plus d. So the way in which you will typically see these systems set up is in the following orientation. I have 2 linear equations where, and don't worry, I'm going to notate these all once I switch back to the document cam. I have 2 linear equations where the slopes are different and the intercepts are different. This makes it so that I have a unique solution to my system of linear equations. You can see that they cross here at 1 point, and because these decimals were chosen for no particular reason, it's just this weird set of decimals floating in space. So long as your 2 slopes are different, you will always get this, no matter how fancy, where they're shifted. Your pair of linear equations will have a unique solution, which is represented by a single coordinate in XY space that we can solve for by various means. However, we want to be aware that there are 2 other possibilities for the orientation of our linear equations in physical space. Here are those other 2 orientations. I could have the following. make that 3. Also make that 3. So here's one of my other possibilities. Could I have somebody describe what's going on? What's it called when we have two lines that have equal slope?
Parallel.
Parallel.
Yeah, these two lines are parallel. And if you attempt to solve this system of linear equations while it's in this form, what do you get?
No solution.
Yeah, you are going to get some no solution type answer. That is to say, if you take and you do the algebra correctly, you would get a nonsense statement, something like 0 equals 7 or 0 equals 5 or whatever. That means that these two lines run parallel forever. They don't cross anywhere. And as such, there is no point in space where these two equations are equal to each other. And then here's our third orientation, which a lot of people forget the third possibility. You're like, well, I guess they either cross or they don't. How is it that you could have a third circumstance? Here is the third circumstance.
They overlap, huh?
Yeah, they overlap with each
Yeah.
other. And so it's not just that they overlap at one point in space. It's that they overlap in all points in space. So instead of us being able to say that like, hey, one point on this graph is the solution to the system, no, it turns out every single point along those two lines is a solution to the system. And as a result, there is an infinite number of solutions. Now, that doesn't mean that every point in space is a solution. For example, this coordinate right here where do you guys see the mouse pointer?
Yeah.
Yeah,
Okay.
we see it.
I wasn't sure if that was caught up in the screen cap, but that's good. That means that this point right here in space is not a solution to the system. Only the points on the line are. So while there are an infinite number of solutions, the solutions are bounded by our linear equation. So let's go ahead and notate that, and then we'll talk about the two ways in which we can solve for the solution of a pair of linear equations, though you already know them, I'm sure. Okay, so in this orientation right here, case 1, if A is not equal to C and B is not equal, I'm sorry, if A is not equal to C, if the two slopes are not the same, this is enough to know that we have one unique solution. That is to say that I have one line in space. Zoop. I have some second line in space, which is not parallel to it. Zoop. And these two cross right here at some unique X and Y combination. If the slopes are the same, if A is equal to C, and by the way, if I'm talking, please feel free to break in if you have a question. If A is equal to C, then this itself is going to branch into two possible combinations. If A is equal to C, then we need to ask ourselves, right, where A and C are the slope, is B also equal to D? If B is not equal to D, we are talking about a set of parallel lines. Also, how does the red look? Does the red come up okay in the doc cam for y'all?
Yeah, looks good.
Yeah, it's fine. Yeah.
Cool. I was working with some friends on my own classes earlier, and apparently this purple pen doesn't show up very well, which makes me sad. Nonetheless, we have two parallel lines in the case that B is not equal to D, and this is going to give us no solution whatsoever. And you know that you are hitting on some type of no solution situation because if you do the algebra, for example, you will get something of the form 0 equals 5 or whatever. You will get some algebraically untrue statement, which is algebra trying to tell you, hey, there is no point in space where these two functions are equal to each other. And then we have our third case where B is equal to D when we write it in the form y equals. This is to say that our two equations are actually the exact same equation in disguise. And so I have my first equation. I have my second equation, which occupies the same space. And so there is an infinite number of solutions. And we say that that infinite number of solutions all lay along the line, whatever one of the equations was. So in this case, you tell me, hey, it's all of the points that satisfy either one of our original two equations. And again, if you do our methods here, there's something you can look for, something that like should trigger in your brain. If you try and solve this system of equations by any of the methods that we talk about today, you will always get that 0 is equal to 0. You will get an algebraically true but boring statement. You're like, wait, what do you mean I can't solve for the point? Why is it just giving back 0 equals 0? It means that your two equations are actually the same equation in disguise. Is this okay?
Yep.
Okay.
Yeah.
So
Mr. Robinson?
yes.
In the notes, when you said if A equals C, and then you put the arrow for B equals D, what did you mean by that?
Oh yeah, so I mean that when you were trying to check which one of these situations is it, just by inspection, right? Just by looking at these equations, it's a two-step process. So the first thing you want to check is, in our little flow chart here, are the slopes equal? If the slopes are not equal, then we're doing algebra and we're going to get an answer. If the slopes are equal, this could mean two different things. The slopes are equal and the lines are parallel, they don't intersect. Or if the slopes are equal and the intercepts are equal, then both of the lines are the same. And instead of getting no solution, it turns out there's an infinite number of solutions.
Oh, okay. Thank you.
Does that answer your question?
Yeah.
Good, good. It's a really good question. Are there any other clarifying questions at this step in the notes before we get into the like solution procedures? No, okay. And so when it comes to solving 2D systems of equations, really straightforward. We have two options. We can either use substitution, or elimination. And I think it's important to know that both substitution and elimination always give you the exact same answer. However, which one you use totally depends on what kinds of equations you are working on. So we'll come back to what I'm about to say later, right? Yeah, we're going to come back to what I'm going to say later, but for today, we're going to be doing both of these methods on our systems of two equations. Typically, you want to use substitution when you're working with nonlinear systems, which is to say any system that has anything in it other than just 3x or 7y or 9z, right? Linear terms have an exponent of 1 or lower and nothing but multipliers. So when it comes to nonlinear systems like a parabola, or maybe you want to know where a line crosses the sine graph, there's really no options other than substitution. However, when it comes to elimination, this is what you want to do for large linear systems. Elimination doesn't work for nonlinear systems, but elimination works elegantly for large sets of linear systems. Okay, so let's go ahead and start off, and we'll do this example both ways for both substitution and elimination. Let's say that I want to solve for the intersection of the system x plus 3y is equal to 8 and 2x minus 9y. I'm sorry, I want to make sure this works out nice. 2x minus 9 is equal to y. Okay. So let's go ahead and be lame, and since we're all at home and we all have access to Desmos, let's just start by graphing it, just so that we know what the answer is before we even start. So I'm going to go to Desmos and I'm going to clear out these lines here. And I'm just going to give it my two equations exactly as they're presented. X plus 3y is equal to 8. And 2x minus 9 is equal to y. Change that to green. And let's go ahead and figure out what happened to our graphs. Wait. Oh, there they are. Okay, so we can see here that we have 2 lines in space. Oh, I'm going to make that undotted. And our answer is what?
5 and 1.
Yeah, the
Oh, yeah.
ordered pair 5, 1, right? So these two intersect in space if we were to take the time to graph these out formally. So we know that the answer that we should get by either method should be 5, 1. So let's go ahead and go through those 2 methods, and then that'll be it for notes for the day, and I'll post the homework and you all can get started on that. And of course, that means tomorrow in class, we'll have a workshop time to work on these 2 methods. In the homework, please do pay attention to which questions ask you to do which method. I'll be grading accordingly. And so number 1, substitution. All that you have to do when it comes to a substitution is you solve one system for one variable. And then plug that into the other equation. And so you'll notice in this system that we're working with to kind of differentiate these two, notice one of these equations is kind of already solved for, right? Which variable is already solved for in that second equation?
Y.
Y,
Yeah. So this second equation is already solved for y. That's convenient. We'll just take this definition of y and plug it into the first equation where we see y. That is to say, x plus 3 times 2x minus 9 is equal to 8. And so from here we can distribute. This is going to give me x plus 6x minus 27 is equal to 8. And now I'm going to combine like terms. So that's going to give us 7x. And then I'm also going to add 27 to both sides. So 7x is equal to 35. X is equal to 5. Neat. And what do y'all think I'm going to do next?
Divide by 7 for the first equation. The top.
And then plug it back into the first equation.
Yeah, so now that I have x, I should be able to take x and plug it into literally either one of these equations. They would both give back the exact same answer, so long as you do the first step correct. But because this one is already solved for y, I'll just plug it in there because that's the quickest path that we have to the y value. So that is to say that it's going to be 2x, and we just found out that their shared x value is 5. 2x minus 9 is going to be equal to y. This is to say it's 10 minus 9 is equal to y. Y is equal to 1. And when it comes to answering these questions, keep in mind that we are talking about literal points in physical space. So the way that we write our answer is correct. This is an ordered pair, so it's 5, 1. Any questions there on substitution? It's a tale as old as time, man. I think this is something that y'all have been doing since probably 6th, 7th grade. Yeah.
We definitely did it last year, but I don't think before that.
Oh, okay.
Yeah, we did.
Bro, this is like elementary school.
Like middle school, yeah.
It
This is like
depends on
algebra range.
where you went or who you had, but either way, this is definitely not the first time y'all have seen this, right?
Yeah, for sure.
Okay.
Yeah.
So now let's go ahead and talk about elimination, which in my opinion, if you are solving linear systems, elimination is almost always the way to go. So what we're going to do whenever we do an elimination is there's kind of setup to it, and it might be overkill for these 2 variable systems, but elimination is the best way to solve 3 variable systems. You'll see that on Monday once we come back from the weekend. But nonetheless, what we're going to do is we are going to write both equations in standard form. And standard form, in case you don't remember, is where we put the x part and the y part on the same side of the equation. And then on the other side of the equation is where we put the constant. And then we are going to make the coefficients of one variable opposite and equal. And this is the key to elimination. We are going to make one of the lead terms, right, the same value, but one will be positive and one will be negative. And this will have the nice feature that when we add the equations together, it's going to destroy that one variable, allowing us to solve for the other one. So x plus 3y is equal to 8. That guy's already in standard form. We don't have to do anything fancy there. X plus 3y is equal to 8. This is already in standard form. X and y are both on the left. Our constant is on the right. So up here, I'm going to have to do two operations to put this guy in standard form. What are they?
Add 9 and subtract y.
Perfect. I'm going to add 9 to both sides. I'm going to subtract y to both sides, and that's going to give me 2x minus y is equal to positive 9. And so, just so that we can keep our two equations distinct, I'm going to call this equation 1, and I'm going to call this equation 2 as we move forward through the following lines. And so I'm going to choose to eliminate y so that we can solve for x first. This is 3y. This is negative y. I'm going to take the bottom equation, and I'm going to multiply the entire equation in line by positive 3. Multiplying a linear equation by a constant doesn't affect it. It's a valid step of algebra to multiply both sides of the equations by the same number. So this is going to give me, in my next line, equation 1 is unchanged, x plus 3y equals 8. And in my second line, this is going to give me 6x minus 3y is equal to 27. Another step of algebra that is always true is that if I have two equations, and if you think about it, this is what that trig identity equation project was all about. Even though the equations that we were dealing with like looked crazy, you could take two true statements, add them, subtract them, multiply, or divide them, and it would still give you back some kind of true statement, no matter how fancy that true statement was. Same thing here. If this is true and this is true, adding them or subtracting them will produce a true statement. So now I'm going to take these two equations and I'm going to add them. What do I get? X plus 6x is?
7x.
3y minus 3y is?
0.
0.
0. And that's why this technique works. That's how you know you have done it correct if you are attempting to eliminate. And then 8 plus 27 is?
19.
Plus.
Oh, plus, sorry.
35.
35.
35. And that exact fiddling with signs is why I actually recommend, you'll see other people do it different. You'll see people who are like, hey, make the coefficients of one variable equal to each other. So some people will be like, oh, this is x plus 3y equals 8. So this bottom one would be, listen carefully to this part, negative 6x plus 3y minus 27. And then instead of adding the equations, you would subtract the equations and you would still get this, but is a lot more of like pluses and minuses to juggle, more chances to make a silly sign error. I do recommend when you eliminate, make the coefficients opposite and equal so that you're just adding. And now I'm going to divide both sides by 7, which gives me back that x is equal to 5. Great, good, excellent. And then once again, I can take this variable and resubstitute it into either line, giving me 2 times 5 minus 9 is equal to y. Y is equal to 1. Same answer, 5 comma 1. Now, the reason why we're covering both of these methods here is that we will be using these in different cases as we move forward. We'll be using elimination in the next section where we're solving not for 2 variables x and y, but for 3 variables x, y, and z. And we'll be using substitution 2 sections from now when we're dealing with nonlinear systems, a case where maybe we have a parabola that is intersected by a line. And if you had a parabola intersected by a line, how many solutions could you get?
2.
Yeah, 2.
2 solutions, and we'll be able to solve for those 2 solutions by substitution. But for right now, I have an example for y'all to do, and then we'll go over it. And then that'll be it for the day. Any questions?
Mr. Robinson?
Yeah.
What would you, like, how would you solve if y in the second equation had a coefficient in front of it?
Oh, it would be the same thing if this here had a coefficient in front of it.
Yeah.
You would still just plug it in, this side would simplify, and then whatever this coefficient was would get divided over. So if this coefficient was 2, then instead our answer would be 1/2.
No, like in the beginning, like when you had to multiply by 3 to make the, make them equal.
Oh yeah, so then you would just multiply by whatever coefficient would be necessary in order to make them equal. So if this was x plus 3y, and for example, this other one was x, you know, I'll just answer your question on a separate sheet. So let's say that I had, also somebody's got a weird echo on their mic. Can y'all mute those real quick for me? Let's say that we had 2x plus 3y is equal to b, just because I don't want to have to solve this out. And then 4x plus 2y is equal to c. In this case, for me to eliminate them, since they have differing coefficients, we're just going to multiply so that in the end, they have the same coefficient, equal and opposite. So I'm going to multiply the first equation by 2, and that will give us a coefficient of 6 on y. I'm going to multiply the second equation by -3, because this will give me a coefficient of -6 on y. So then this will turn my system into 4x plus 6y is equal to 2b. And my second equation becomes -12x minus 6y is equal to -3c. And from here, when I take these two and I add them, the y's will cancel. Is that okay?
Yeah.
Okay, good. Good question. Okay, yeah. Let me ask y'all to solve the following system of equations. So for example, solve by elimination x is equal to y plus 3, and 4 is equal to 3x minus 2y. Quick, do that as quick as you can. Take maybe 60 seconds on it. And in the meantime, I'll do a calculator aside for those of you following along at home with such a calculator. When it comes to these you know, I have a question. So given the choice when I do these lectures between on-screen real calculator and digital calculator, which is better? Let me pull up digital calculator so that you know what I'm talking about. I don't care. I just want these instructions to be like followable at home. So let me go ahead and share my calculator. Do y'all see that?
Yeah.
Is that, can you see the mouse pointer on the screen?
Yeah.
What's cooler, the on-screen my physical calculator or this emulator of a calculator?
Yeah. Probably this one.
Yeah?
Yeah, I can see this one more.
Okay, yeah, we'll do that then. So, hey, just so y'all know, your calculator, you can use it to solve explicitly for the answer to an ordered set, except to do that, you would always have to type it in the form y equals. That's just how your calculator demands that this stuff goes. So let's say that we were doing the previous question, the one where the answer was 5, 1. I would have to take both of the equations and write them in the form y equals. And I could, you know, write them up here. So that second equation was y is equal to 2x minus 9. And then that second equation, what would that be if you wrote it in the form y equals? You have to move the x over to the other side. So you would get 3y is equal to -x plus 8, and then divide both sides by 3. So you would get y is equal to -1/3 x plus 8 over 3. Yeah, is that okay?
Yep.
So in parentheses, I would get -x divided by 3. So there's my -1/3 x plus 8 divided by 3. And now I can ask my calculator to, hey, please graph these for me. And you'll notice the calculator is going to graph them the same as it did in Desmos, just a little chunkier because it's, you know, not internet based. It's like whatever your calculator can do. But the reason why I'm showing all this is, you know, you can do this, but please know that you can also hit second, calculate, intersect. So I'm going to hit enter on that. And now I'm going to move the cursor over, and you can see as I click left and right here, it's going to move the cursor towards that point. Get it as close to the intersect as you can. Hit enter. Get it as close to the intersect as you can, and normally it'll already start off pretty close. Hit enter. And I'm going to hit enter a third time. And oh, look, it's exactly 5,1. This is tight, not just for linear equations, but when we talk about our nonlinear systems, fancier stuff, this will be useful and in some extreme cases necessary. The other thing that you can do to try and, 1 second, then I'll take that question, to look for a solution is hit second table. And you'll notice that if I look at the table points, if the answers happen to be integers, because it's a high school math textbook, if I scroll down here to where x is equal to 5, what do you notice about the y values?
They're 1.
They're both 1, which is another way that you can look for a solution. Though I wouldn't recommend this second technique unless you know for some reason that your answers will be integers. Otherwise, you won't be able to see where they're equal in the table. There is a question out there. I missed a raised hand.
Yeah, Mr. Robinson, I had
Yeah,
a
what's
quick
up?
question.
Mm-hmm.
You know how you're multiplying in the elimination method?
Yes.
Could it be done by division too?
Yes. Which, if you think about it, multiplication and division are the same thing. To multiply by 1/3 is the same as dividing by 3. So I would recommend don't divide anything. Just multiply by the correct fraction.
Okay, thanks.
Tight. Okay, let's do this question and then we'll be done for the period. And like I said, you know, tomorrow I won't talk anywhere near as long. Tomorrow will be workshop. So have your homework ready to go. And if y'all have any questions, you just drop them in the chat and I'll solve them here. Be sure to mash like and subscribe on the YouTube channel, by the way. I uploaded the first set of videos yesterday. It's actually real easy. So all of these videos will be going up in case you ever want to review something you missed. Nonetheless, we're going to do this by elimination. So like I said, what we want to do is we want to put both of these in standard form. We want to put both of them in a way that gives us that the x's and y's are on the same side and the constants are on the other. This guy is already fairly standard, so this guy needs to be hit with an algebraic step. We're going to subtract what from both sides?
Y.
And I recommend doing this. It's overkill for 2 variable systems, but you'll see when we get to 3 variable systems, it might be important to keep your pieces labeled. Equation 1 is going to become x minus y is equal to 3. And then down below, I'm just going to flip the sides there. So equation 2 is going to become 3x minus 2y is equal to 4. Now, would y'all like to eliminate x or y?
Y.
Yeah,
Let's
sure.
go ahead and start off by eliminating y. And to do that, I'm going to multiply equation 1 by 2. And so this is going to give me, equation 1 is 2x minus 2y is equal to 6. Equation 2 is 3x minus
Shouldn't it be -2?
Yeah, we
should
shouldn't
be -2. -2. And so this is actually -2x plus 2y is equal to -6. That doesn't show up very well. Hold on, let me fix that. Is equal to -6. And then the bottom equation is unchanged. 3x minus 2y is equal to 4. And now I can take these 2 equations and I can just add them. And so what do I get for my x's?
X,
Just x plus 0 is equal to
2.
-2.
Yeah.
And
Yep.
so x is equal to -2. Great. And now which one of the equations should I plug it into up above?
1.
The first one, the x equals y plus.
Yeah,
Yeah.
literally either one. And if you're just trying to get the correct answer as quickly as possible, you know, just pick the one that has a simpler form. And so this is to say that -2 is going to be equal to y plus 3. I'll subtract 3 from both sides. Negative 5 is equal to y. And so our answer is the ordered pair, negative 2, comma, negative 5. Are there any questions about today's lesson?
Yeah, Mr. Robinson. So when you're solving by elimination, you always multiply one of the lines with the other line's constant for the y.
Whatever is necessary to make the coefficients equal. So generally, yes,
Okay.
but before we started this question up in the line above, one of my y's was 3, the other y was 2, and so it wasn't enough to multiply this one by 2. I'm sorry, this one by 3. You also had to multiply the first line by 2. So here, both of them had to be multiplied so that one could be positive 6 and one could be negative 6.
Oh, okay.
Good question.
Thank you.
Any other questions out there? No? Okay. That takes us to the end of our regular class period. Feel free to pack up, head out, have a nice day. I'll see you tomorrow. And when I see you tomorrow, we'll have a warm-up of this nature, probably 2 questions with a little bit of graphing. And then we'll have the rest of the period to work on the current homework assignment together. Just ask and answer questions. Y'all have a nice day. See you then.
See you, Mr. Robinson.
Peace.
See you.